we're starting talking about the protocols that are used when the packets are routed around across the globe.
Sir,
Yeah, yeah,
so can you give me the permission to record?
oh sure. However, in the beginning, we should understand that in the case of interconnections of different nodes for uh, digital communication or for exchange of packets of information, there are certain protocols in use which are layered to get them more organized. The activities are categorized with layering. Layering uses uh, I mean, the process in uh, in a class. I mean, in some kind of classification that put them in order. Say a particular layer may do a particular part of the whole process and then forward it to the next layer. The next layer will do the uh, next stage of the process and then forward to another layer. So if you put them in a layer, then it is more organized and a chronological order can be better maintained. Now this is how it is commonly uh, layered, and the original layering to be used for the interconnection across the globe, which is the internet. Internet is a particular type of interconnection, a particular, not type, a particular interconnection among millions of nodes across the world. So for internet, the original layering uses something called Open System Interconnection Model, or OSI model, and it has 7 layers at both transmitting and the receiving ends. The transmitting side starts from the top. The application is actually the software that we use. Uh, some software have interaction with the uh, human being, and sometimes it may not be, but there's a software or uh, sometimes more than one software which performs these application layer activities and then generate uh, the packets of data. For example, if you were seeing some data from some website, so your Mozilla is a web client which works at the application layer. So to look at the left side, let's say that the left side is the transmitting side and the right side is the receiving side. And the application layer, Mozilla is working and it is generating a query for some particular web page. So this query is put into a data packet and it is then forwarded. Presentation and session layers we won't discuss in detail because these, I mean, the top 3 layers mostly belong to the computer science engineering or software engineering guys. They they work with them. I mean, at the application layer. The packets are whatever it comes from the application can be needs to be organized or they need to be rearranged sometimes. Okay, so this kind of things are done by this next 2 layers, presentation and session. And finally, the transport network, the bottom 4 layers are a lot of times handled by the people with electrical engineering background. So this can be our focus. By the way, in this wireless communication course, we are going through this stuff because of two-fold reasons. The first one is when you design a wireless link, there are a couple of, there are, I mean, uh, sometimes it requires, then you need to know how the packets would be routed at the back end. Within the wireless, you are working on just one part of the whole uh, packet routing data, uh, packet routing path. Okay, so and to have an effective design for this wireless link, a lot of times it is required that you have some idea, at least to some extent, you know what's going on beyond this link. So uh, this is one reason for this discussion. Secondly, for wireless cases in uh, I mean the original protocols can need some modifications. Uh, for example, right now we're going to discuss two particular protocols, IP and TCP, but they need some modifications when you have a wireless link. If you don't have any wireless link in the whole data routing path, you don't need the modified versions. If you are just using Ethernet, then there is no wireless link in the whole data routing path. So it's all good. But if there is a wireless link, you may need some modifications of the of some core protocols working across the link. So we will discuss after we discuss this basic uh, pa- idea of TCP/IP. We will also discuss what modifications you need when you have a wireless link and you have a mobility. When you have a wireless link, it is possible to have mobility. So then you come across some new requirements. Uh, Now, in this part, we will discuss the activities of transport and network layers. Uh, so layer 3 and layer 4. But OSI model is the original model, and there are different variants of it in use. So you will find in different stages of your lives, different variants of it, but usually all with this 7 layers concept. Okay. Now, we can see that in the network layer, layer 3, IP, Internet Protocol, is what is used. And we'll discuss TCP, which is used at layer 4, in the transport layer. However, TCP has an alternative. UDP is a simpler technology, simpler protocol, which can be used for some type of applications. But if you have complex requirements, then you need to use TCP. So for network layer, there are two options, TCP and UDP. But for transport layer, but for network layer, it is now all IP. There is no other option now. In the past, there was the protocol extra 2.5, but now, those things are obsolete. IP is the only option. So whenever we have packet switching, when we see the packet switching, uh, for circuit switching, you have a continuous flow of the packets in order. You have some reserved resources and you send the data packets. You packetize, but you send them one after another. They will not go out of order because you have resources reserved. So you just put them there. But in the case of packet switching, you don't reserve. So different packets could be just when they arrive, you find out, you look for resources, you may have to wait, and Once you get hold of some resources, you put the packets, so the new packets may take another route, completely different path it may take to get to the receiver. So it's all haphazard, and I mean they can arrive at the receiving end out of order. Okay? I mean not in the same order as they were transmitted. Now on the transmitting side, as I said, it flows from top to down. You The application layer first generates the data packets, and presentation session layers organize them, and we'll discuss what the next two layers do. Okay, and finally it gets to the physical layer, and physical layer transmits. It's responsible for the necessary processing so the data can be transmitted, and via uh, many other nodes or some networking path, it will get to the other end, and the physical layer of the receiving side will receive. Then it does an opposite type of process, and it forwards after the physical layer of receiving side completes this process. It forwards to the layer 2, then layer 3. So it goes from down to top, and finally the software working at the application layer receive. Say if you are fetching some data from a website, there's also a, application running at the web server. So the web server receives the packet, and the web server then puts the web page information that you have uh, sought for uh, into packets they put. So those packets will then be again, I mean, sent to. So the web server is now the transmitting side. So it will these packets will be processed from top to down and then sent to your computer. Okay. So it will your computer is then receiver. So the web page information comes back to your Mozilla or web client software, and then it displays. Okay. Now uh, the IP layer, we already started discussing it as the primary purpose to allow every node to have a globally unique address or unique identity. So within the whole world, wherever you want to, you can send a data packet. Every node is uniquely identified with an address. So you use the address like the postal system to forward your data there. This address called IP address uh, has some hierarchy. You see that for forwarding at different stages, you need some hierarchy. Like you understand that for postal system, there is a hierarchy of the address. There is a country name and say a district name in our country, then a city name, okay, then the road uh, name, the house number. So there is a hierarchy. So when somebody from UK is sending a letter to you, the letter will first be forwarded based on the country level uh, uh, part of your address. So it will come to the central uh, hub of our country. Then it will forward it to the hub of a particular district. Then, so it will once it gets to the country hub, that will work with the district level address. Okay, it will not go far into the address. It will forward just based on the district part of your address, and from district it will be again forwarded to the particular say city, so on and on. So you need some hierarchy within your address. So similarly, the IP addresses use some hierarchy, and the IP address is in version 4. For IP protocol, there are two different versions: IP version 4, IP, okay, IPv4, and IP version 6. In IP version 4, the length of IP address is 32 bits. In IP version 6, it is 128. So this IP, say, assuming IP version 4, the 32 bits long address use a part to indicate the country. And this is why experts who work in this network area who have been in this area for a long period can understand just looking at the IP address where it is from. I mean, I saw some people to be able to do that. Oh, okay, they know that, oh, this IP address is from Korea. Okay, they have got some idea. To some extent, they have idea. So, so this is something I'm telling you so that you understand that within IP address, definitely you need this kind of uh, zone-based hierarchy. Now, to discuss the activities under IP, we will discuss the header of IP packet. Uh, the IP packet is organized, say, from an upper layer on the transmitting side. It gets whatever data that need to be processed and then forwarded. So the whole of the data it has received from its upper layer will be put into this blue part. The actual data to be carried is called payload. In a data packet, the data you want to carry within the packet is called payload. And you need some control information, which is typically put in the beginning. So it is then called header. So the white part represents the IP header. You may also have some fields at the end of the payload. Some tail fields can be there, but in TCP or IP, it's all used in the header, in the beginning of the whole packet. So an IP packet is formed this way. Uh, in addition to the data payload, you use this kind of header. And the mandatory fields are take up 20 bytes. You see the 32 bits and then 5 rows. So 8, uh, 4 bytes in every row. So 20 bytes. And there can be some optional fields, but usually these optional fields are not used. So usually you have 20 bytes of IP header in IP version 4. Now look at the bottom two mandatory fields, source address and destination address. So when you want to send a packet to somebody, the IP address of your destination is used here, and your own IP address is also put there. Okay. The data will be routed on the way, and this is how you send the packets on the link you are connected to. And the link will be connected to some router, and that router will be connected to another router. So the whole world has a interconnection of many different routers, and they keep routed from router to router, and finally it gets to the router that is connected to your destination device, and then that is forwarded to the destination. So every time, every router forwards the IP packet looking at this destination address. So it checks the destination address of the IP header. All routers do that. on the way, and then decides which way to forward it. So every router has multiple input ports for data to be received from different directions, and also multiple output ports to forward the data in different directions. In different directions, they are connected to routers in different geographical areas. So this is how via different geographical path it gets to the destination. And the router uses a table which is called routing table or forwarding table. So the table is updated once in a while, depending on some changes in network conditions. Please give me a second. I need to turn off the AC. I'm sorry. Uh, so the destination address help the routers decide which way to be forwarded next. And the source address is also included because, as I already wrote there, the receiver, first of all, can decide whether or not the packet should be received. For some security reasons, it may not, it may have some IP addresses blacklisted. The ranges of IP addresses blacklisted. So if it is a safe IP address, uh, it will receive the IP packet, and also it knows where to reply. So when you are fetching data, you're sending a query to a web server. Reading from this source address, it knows where to send the web page information in response. So when the web server sends an data, putting them in an IP packet, it uses your address. I mean, when you are sending, the web server IP address was used in the destination field, and your IP address was in the source field. And the web server responds with opposite uh, use of the fields. The web server address will then be source, and your address will then be the destination. So the packets will then be routed back to you.
Sir, can you repeat this part?
Say you are just connecting to some website, and you click on a link on the website to actually request another web page. So once you click the link, you send a query to the web server to send you another web page information. So your request will be put into an IP packet like this, and the IP address of the web server will be used in the destination address field. And your own IP address will be included in the source address field. Then the data payload includes what web page you are requesting. Once the web server receives this IP packet, it knows from the data payload what you are requesting. And from the source address, it is see the source address has not been so far used in data routing until your IP packet gets to the receiver. There is no use of the source address. All the nodes on the way, all the routers on the way work only using the destination address. It knows where to send. It just like in the postal system. The postal system does not need to know where you are sending it from, right? It will just look at the destination address and decide how to route the later. But once your friend in a different country maybe is uh, receiving the letter, okay, at the first glance he will be interested to know who has sent it. So he look at the source address and then he knows, oh, it's my friend, okay, from that country, he sent me. So until it gets to the web server, there is no use of your source address field in the IP packet. But the web server finds out that this web page information has been requested. So that web page information is put into an IP packet, and then it forwards this IP packet back to you. So the source address of your query packet will now be used as in destination. It will be now put in the destination address field of the packet, okay, that the web server is sending to you. And the web server will include its own address in the source address field. So, I mean, in the reverse direction, the addresses exchange their positions here in these two fields. Is it clear now?
Yes, sir.
Well, uh, however, when you access web server, I mean, this is something I happen to discuss in other sections, although it is not included here. When you access a web server like, say, yahoo.com, the IP address of this server you don't know, and it's not possible for you to memorize the IP address, right? So similarly, say msn.com, cnn.com, all these web servers have some particular IP address, but it's not possible for people to memorize these IP addresses. But people can memorize the names, yahoo.com, cnn.com. Uh, so you need to actually translate between the name and the IP address before you can send an IP packet there. How can it be done? This is why in every um, service provider premise, there is a DNS server. For example, in our IoT campus, okay, the ICT department is providing the service. So a few types of servers they need, like they have a web server because IoT has some web page. They have some mail server because IoT has some web mail. Okay, but it also has some DNS server. So when you are writing yahoo.com, your computer will first fetch the corresponding IP address. It will send a query to the DNS server. It is a local server within our ICT center. The DNS server is constantly updated with the list of IP addresses for different names. So when you send yahoo.com to DNS server, it will return you the corresponding IP address. So from then on, you can just you can keep using this IP address in the IP packets. You no longer, this communication with DNS server is just an one-time activity. Okay, you just fetch the IP address for a particular website name, uh, and then you start using that IP address. Okay, is it clear? Okay.
Yes, sir.
If anything is not clear, please let me know. And I know that many of these things, at least some of you already know. These are some basic networking ideas. Okay, the version field uh, tells you whether it is IP version 4 or 6. Uh, IP version 5 was used only for experimental or research purposes. Then there is field header length, H length. This field tells you how long the IP header is. Since there can be optional fields, the length of the IP header is not fixed. And so it is also not fixed where the actual data payload starts. So from header length, the receiver can come to know how long this part is, and from within the IP packet, it starts considering the data payload, or it starts reading the actual data content right after the header. Okay, so the header length field also actually indicates where it should start the data. Where it should start reading the data payload. Then type of service, this is not very important. TOS field gives a priority. I mean, it is possible that some IP packets can be put in priority. Well, we will have to discuss something called network congestion in pretty good detail when you discuss TCP. But let me tell you that as the packets are routed via in the packet switching network, PS. Okay, CS is simple, but in PS, the way they're routed at different routers, packets are coming. But at the output port, some links may be already busy, or the rate of incoming flow can be higher than what it can accommodate at the output links. So a router may have to then store the data which it cannot currently forward, and it will put them in buffer. But if the incoming flow it does not slow down, at some point of time the buffers may overflow, meaning that some packets will be dropped there, or you lose some packets. This packet drop is a very common situation, and this is something like we have a traffic jam. So this is called network congestion. And in our traffic jam, we don't throw away the cars, but here they have to throw away the packets which when the buffer overflows. Okay. Now with TOS, you can give some packets to have some higher priority, and they can be forwarded, keeping others in queue. Okay, so it's possible. Say when some important type of, say some important international organizations are communicating. Okay, so their IP packets may be given some higher priority. Well, the length field tells you how long the whole packet is. The header, the payload has a maximum size. The total packet, okay, length can be at most 65,535 bytes, including the header. And the field is 16 fields, the length field is 16 bits long. Okay, so which limits this maximum size? Okay, but that's pretty big, more than 65,000 bytes. Okay. Then there is a protocol field which tells you which are the upper layer protocols, TCP or UDP. And there is a field checksum which confirms that the receiver can read properly at least the IP header part. The data may get corrupted, some bits may be flipped, but there can be some ways to overcome this kind of errors, or some applications can even tolerate some errors. But the header must be read correctly at the receiving end. Otherwise, for example, if the source address is not correctly interpreted, the next actions will be wrong. So we need to confirm that the header part is correctly retrieved. This is why uh, on this whole 20 bytes of header, some particular type of calculation is done, which results in 16 bits of field. And um, in this case, actually, this calculation procedure is called checksum. The result is called checksum. So this checksum is included here. Similar, so these are some error detection mechanism. There is another popular error detection mechanism, CRC, cyclic redundancy check. Maybe write down this term. Because checksum and CRC are actually the only two popular error detection mechanism I have seen. Okay. There can be some uncommon methods, but usually you would find either checksum or CRC. So they both work on the whole content and then generate a few bytes. At the receiving side, the receiver will compare, it will do similar kind of calculation and then check whether or not the calculated checksum matches the received checksum. Okay, so if it matches, then the receiver knows, okay, the whole 20 bits have been, the header has been received correctly. So this is how, if it is not received correctly, okay, so it should throw away this packet. It should not accept this packet. It cannot work with this packet. So whether the packet is acceptable or not, okay, the header part at least has to be correctly received. So CRC is stronger, but checksum is easier to calculate. Time to leave, a TTL field is there. It's also not very important. Sometimes it may happen that a particular IP packet has fallen into a loop. It cannot go out of a loop. It is forwarded by different routers, but it is coming back to the same router and then again forwarded and again coming back. So that just consumes resources for nothing, for no benefit. So what is done, every time the packet is forwarded by a router, it decrements the value of TTL. The whole packet routing starts with certain value at TTL, so that is decreased by 1 at every forwarding by a router. If TTL falls to 0, then it is recognized that the packet has been probably in a loop, so the packet is dropped then. The default value of TTL is 64. Okay, now we need to talk about the second purpose of IP, fragmentation. Well, in some cases, your lower layers may have a limit in the, a smaller, every link has certain limit of the packet size. But the lower link may have a smaller packet size limit. For example, Ethernet has a maximum limit of 1500 bytes. So your IP packet may, generated by network layer 3, may be as big as say 20,000 bytes, because the maximum size allowed is 65,000, more than 65,000 bytes. So if we have say 20 bytes long, 20,000 bytes long, or maybe as okay 15,000 bytes long IP packet. When it comes to the physical layer, Ethernet cannot tolerate a packet size bigger than 1500. So you need to do, you need to split this 15,000 bytes long packet into 10 segments and then forward. So a segmentation of an IP packet may be a requirement because of the restrictions in the lower layers. But you need to definitely uh, reproduce the IP packet at the receiving end. So how is it managed? Well, there are three different fields in the IP uh, packet information, IP packet header. Ident, they are all in the second row. It's ident field, offset field, and one of the flags. A flag means you use some just bits, ones and zeros, for some indications. When you use 1, it is called set. The flag has been set. When you use 0, the flag has been reset. These three things are used: flag, ident, and offset. But we'll explain it using uh, an example. By the way, the maximum packet size in Ethernet is 1500 bytes. But Ethernet works at the bottom layers. Actually, Ethernet protocols cover the bottom two layers, the data link layer and the physical layer. Well, the at this bottom layers, the maximum size of the packet is called maximum transmission unit. Because this is the permissible maximum size which you can use for transmission over the link. So MTU is a term commonly used. Now let's use an example. In this case, the MTU is 512 bytes. By the way, we are covering the stuff from the textbook uh, Computer Networks by Larry Peterson and Bruce Davis. And these books, the computer network books, use one of the two approaches, top to down or down to top. So you start explaining from the application layer and keep explaining how things are processed at layers one after another and end up with the physical layer. This is called the top-down approach for explanation. Another way is to start with the physical layer and keep explaining different layer activities, ending up with the application layer. This particular book uses down to top approach. Okay, so the books explaining the networking protocols have one of these two approaches, top down or down top. Well, in fact, usually the electrical engineers prefer the down to top approach. They feel more comfortable down to top approach, because then it is, the lower layers are, first explained, which are more of their interest. Okay. On the other hand, the people with computer background usually prefer a top-down approach for explanation. Okay. Well, in this example of fragmentation, see, an original packet has been generated with 1400 bytes in the payload. And in the identity field, there will be some number. This is the number. In the identity field, there is some number. So what is done? The packet can be segmented, and these segments, the early segments will be given the maximum possible size. I say that the MTU is 512 bytes here. So in the first segment, you put 512 bytes. Okay. You're still with quite a bit of data. So in the second segment, you can also put 512. So that has already covered 1024. Now you are not left with that much. You're only left with 376. So in the third segment, you put it. So that completes the whole content. Now, in the first, except the last segment, always use a value of 1 in this flag. Okay, so that there are certain flags options here. So a flag, one of these flags is used for segmentation purpose. So this flag is set to 1, but when it is 0, then the receiving side can understand that this is the last segment. There's no more segments. Okay. Now, finally, the offset field. If I explain, then you understand the whole segmentation procedure. In the first segment, the offset field will be set to 0. Then, for the second segment, you need to check how much data has already been covered. In the first segment, 512 data bytes were transmitted. So, I mean, this much data has already been covered. Now, this 512 is divided by 8. This 8 is a standard factor for segmentation purpose. So it's always 8. So once you divide by 8, you get a number 64. So in the offset field of the second segment, you use a value 64. In the second segment, you're using 512. So when you are creating the third segment, 1024 data bytes have already been covered. So once you divide 1024, you get 128, and that you use in the offset field. Okay. The next field segment could have 1024 plus 1376, and this number divided by 8 for its offset field. But you don't need any other segment, and the receiver can understand that you don't have any other segment because this flag is reset here to 0. Now probably you understand how the receiving side can combine the segments and reproduce the original IP packet. Is it clear? You can put them in right order. And then this is called concatenation. When you put a number of segments together to create the bigger one, it's called concatenation. Any questions so far? Let me check with you guys. Is there anyone who is still awake? There is none.
Yes, sir.
No one is. Oh, you are awake.
Yes, sir.
Oh, okay. Okay. Great. Okay. There are at least some people who are still awake. I love them. In IP version 6, the address field is 128 bits long, and this was the primary motivation to introduce another version. Well, the 32 bits long address needs to be used to uniquely identify, globally, uniquely identify every node. But internet is growing so rapidly, increasing the number of connected devices, that the possible combinations will run out if it is only 32 bits long. Well, with 32 bits long address, the number of combinations possible of ones and zeros is close to 4 billion. So that's a huge number. So you can argue that why we need, uh, even longer. This looks sufficient. It is not for two reasons. First of all, in future, there will be many other devices. A guy may buy, say, 20 IT devices or 30 IT devices when he comes back and put them in his house for some particular purpose. So maybe for activating different, uh, I mean, different automated operations. Say, in the, some lights that will glow automatically in the parking area or in the backyard, or say some regular accessories at home may have some automated services. We'll later have some discussion on the IoT applications. But you see that this is how the number of nodes would be very large. IoT means the device has to be connected to internet. So it has to acquire a globally unique IP address. And so, in future, at least, even if it is not now, in future, people will definitely run out of uh, available IP addresses. So this is why the address field has been increased to 128 bits, which allow, if you use all the combinations ones and zeros, the number of possible combinations is 3.4 into 10 to the power 38. So maybe every dust on the world can be connected to internet. However, you need to understand that the address cannot be used 100%, address space cannot be used 100% efficiently, because you need some hierarchy in the address for this area. So the early bits of whole IP address will be the same for a particular large geographical area. The later bits would be different. And when you get to another smaller region of that whole big area, some other early bits, next to the very early bits, will be same over there. So this is how, since you need this kind of hierarchy, all the possible combinations cannot be put into use. So 4 billion nodes cannot be connected in IP version 4. It will be much less. Similarly, this 3.4 nodes cannot be connected. It will be much less. But it is still very big when you use IP version 6. And IP version 6 address includes the MAC address. Like, say, for Ethernet, within this Ethernet is used over a limited area, uh, or the LAN. Uh, every user acquires a MAC address. This is 48 bits long address. So the user in its IP address includes this 48 bits long address when it is IP version 4, IP version 6. So you have long 128 bit, and you have to have a unique identity. So the MAC address already gives you some level of unique identity within your small LAN area. You have a unique identity there. So that is included in IP version, but it wasn't possible in IP version 4 because IP version 4 is smaller than this MAC address. This is the IP header for IP version 6. There is no optional field. So the length of the IP header is fixed and it is 40 bytes. If you just count the number of rows, you'll see that there are 10. Okay. So you have 40 bytes long address. Okay. Primarily because you have large source and destination address. So the other fields, I'll just explain a few from there. You have version field. The traffic class and flow level, they relate to some quality of service, maintain some quality of service. They are used similar to priority. Okay. And the next header field is similar to the protocol field of IP version 4. It includes whether it is TCP or UDP. Now, the IP version 4 is still used much more widely. IP version 6 has still very limited use, especially in our country. More than 90% use are actually IP version 4. However, there can be IP version 6 packets sometimes when your networking facilities support only IP version 4. How is it handled then? It's very simple. It's called tunneling. You tunnel the IP version 6 through this part of your network, which supports only IP version 4. At the other end of this part, the network, you may have IP version 6 supported. What is done is the IP version 6 packet is treated as the payload of an IP version 4 packet. The whole IP version 6 packet, including IP version 6 header, is put into the data payload. And an IP version 4 header is added. This new IP packet is then forwarded over the IP version 4 supported part of the network. The source of address, the IP addresses for the IP version 4 are calculated based on whatever IP version 6 addresses you have there. Based on that, once they are calculated, you can create this IP version 4. So it is called encapsulation. IP version 6 packets have been encapsulated. Once it gets to the other part, other uh, side of this part of the network, IP version 6 can again be supported. So it is then decapsulated. The IP version 6 packet is taken out, uh, throwing away the IP version 4 header. And then this IP version 6 packet is forwarded. This is called tunneling. You call tunnel, you are just tunneling the IP packets via this part of the network. You can check your IP version, IP addresses, and some other information if you type in command prompt. You need to type in ipconfig. If you type in ipconfig by all, then you can also see other addresses like the DNS server address. So when your internet connection is configured on your computer, it should be given the DNS server address. Okay, so your network configuration includes this DNS server information, so you can reach the IP addresses of other computers that you want to connect to from this DNS server. Any questions? IP is complete now when I discuss TCP. Any questions? Okay, if not, we will discuss TCP, but the last 5 minutes we'll be using for attendance. Well, for TCP, there are five different purposes. The bottom two may be combined. Okay, some books will tell you that there are four major purposes. The first one is in order delivery, which is to some extent already probably clear where you need. The different IP packets are independently forwarded by the router. So, if two packets may have arrived with the same destination IP address, you're sending something to some, say, an FTP server or some web server, mail server. You're sending a query. So it is now carried by two IP packets with the same destination address. When the network forwards the first packet, it uses certain direction. It puts into on a particular output port. So it is forwarded in particular direction. But then the network condition changes. This link gets crowded. So the network, the router updates forwarding table, and the same IP address now comes with a different output port. So the next IP packet is forwarded in other direction. So via some other routing path, it again gets to the destination address. So two packets were generated together, uh, but maybe the second packet, okay, it goes faster. The path uses some shortcut, it goes faster. So the second packet uh, arrives earlier than the first. So they are then out of order. So this way, in fact, the difference in the latency, latency means how long it takes for the router for packets to get routed uh, and get to the receiver. The latency can be actually significantly high, putting the packets in completely out of order, or I mean, too much out of order. So you need to put them in the right order to get the actual information, right? So this is taken care of by TCP in our, this is in order delivery of your information. And the point is that, as I said, that's the routers can drop some packets or can lose some packets on the way because of congestion. These packets then should be retransmitted by the sender to make sure that the receiver gets they're lost on the way. So to recover the complete information, some packets in the middle which are lost need to be retransmitted. Not all packets, but only those packets which have been lost, which have been dropped by the net router, should be retransmitted. Uh, so the sender side actually needs to be aware of what is going on there, what has been received successfully and what has not. So the condition at the receiving end should be known to the sending side so that it can retransmit the necessary packet. So this is taken care of again by TCP, and this is called reliable transmission. Okay, you maintain the reliability of the delivery of the packets. Questions? We'll go from here the next day. Inshallah. Questions?
No, sir.
Okay, then let me take the attendance. Okay, 101,
Present, sir.
102,
Yes, sir.
3,
Present,
3,
sir.
5,
Yes, sir.
6,
Yes, sir.
7,
Yes, sir.
8,
Yes, sir.
11, 11,
Yes, sir.
12,
Yes, sir.
Yes, sir.
13. Okay,
Yes, sir.
okay. I mean, are you 13?
Yes, sir.
Okay, 14,
Yes, sir.
17,
Present, sir.
18,
Yes, sir.
19,
Yes, sir.
21,
Yes, sir.
22,
Present, sir.
25,
Present, sir.
31,
Yes, sir.
32,
Yes.
33,
Present, sir.
34, 34,
Yes, sir.
36,
Present, sir.
37, 37, okay, 38,
Yes, sir.
40,
Yes, sir.
41,
Yes, sir.
44,
Present, sir.
46, 46, 47,
Yes, sir.
49. I could not
Yes, sir.
hear from 46. Okay, 50,
Yes, sir.
51,
Present.
52,
Present, sir.
55,
53, sir.
sorry, 53,
Present.
54,
Present.
55,
Present, sir.
56,
Yes, sir. 56.
57,
Present.
60.
Present, sir.
Thank you. Thank you so much.
Sir,
Sir,
one,
this
sir.
way was
Present.
sir,
Yes, sir.
146 is present chat box. Sir, 146.
One. Okay, give me a second. 46.
Sir.
Okay, yeah. Yes,
156, that late. I cannot remember, sir.
156 is given present today.
Sir.
Yeah,
One.
my record there, I saw late.